Okay. Ayang's not here anymore. Just give it to me. Ayang's and not us.
Vinci.
Ayang 和娜娜有。Okay. Let me give you the answers first.
Okay.
Alright. Let me give you answers first. So question 1 to question 5. CAAAB. CAAAB. Question 6 to 10. CCABB. Question 11 to 15. CBBBB. And question 16 to 19. CCBB. Anything to talk about? Any questions?
Number 3. Number 3.
Okay. Number 3. Question 3, question 10, 12, 13, 18, 15, Emma. Okay, let's look at question 3 first then. Can I erase the answer now? You guys take down the answers. So let's look at question 3. Question 3, a runner starts from rest and accelerates at a constant rate throughout a race. Which graph shows the variation of speed with distance traveled x? Which one did you choose? B. Speed, distance, not time. Be careful, guys. It's velocity distance graph, not velocity time graph.
我看到 S 就说这是碳。
So S equal to it's constant acceleration, so we can apply what? What can we apply? Suva, right? It's asking relationship between V and S. V and S. We don't know T, so we need to use a Suva equation that without T. Which one? Which Suva does not have T? V squared equal to U squared plus 2AS, right? Isn't it start from rest, so U squared equal to 0, which means V equal to root 2AS. And S is your independent variable, so you got root 2A, which is a constant, times root S, which means this is a y equal to root x function. Get it? Be careful. Okay, it's not difficult. You're just like taking S as T. Question 10. Question 10. Question 10, let's look at it. So, an object is released from a stationary hot air balloon at height h above the ground. An identical object is released at height h above the ground from another balloon that is rising at a constant speed. Air resistance is negligible. What does not increase for the object released from the rising balloon? Okay. Number 1, the distance through which it falls. So basically, let's draw two hot balloons. We have one here, we have another one here. This one is stationary, right? It's just floating in the middle of the air, right? But this one is moving upwards with a constant velocity, with a constant speed. So it's moving upwards. Do you guys still remember what is inertia? Chloe, what is inertia?
When the it's when an object stops
Inertia is the property that any object has to maintain its original motion. So if it's moving, it will try to keep moving in the same direction at the same speed. If it's at rest, we will keep trying to keep its rest, right? So yes, that's what. So that's inertia, right? So if you release a stone from the rest one, that means the stone would start from rest, right? It will directly fall. But if you release a stone with this moving upward hot balloon, the stone has already moving together with the hot balloon, which means the stone has already have a upward velocity v. When you release it, it has to go up and gradually slowing down its velocity to 0 and then go down. Does that make sense? So what's happening is, let me grab two balls. What's happening is one ball is like that, directly going down. Another ball has the initial velocity going up. Yeah. Right? So that's what it happened. One directly go down, the other has an initial velocity. So the distance through which it falls, will it increase? Yes, because you go up and then you go down. Distance will increase. Time taken for it to reach the ground. You go further, would you take longer?
Yes.
Yes. The speed with which it reaches the ground, will it change? So right now, think about this. This one starts from rest. This one goes up first. And then when it comes back to here, does it already have a velocity? And then at the same level, it already has, when it go up and go down again, it already has a velocity. So when it hits the ground, it's going to have a greater velocity than this one. Does that make sense? Okay, very good. So acceleration, if we ignore air resistance, isn't it both of them free fall? The only force that acts on them are gravitational force. So the acceleration due to gravitation, both of them is g. So d is correct. Right? D is not gonna increase. Okay? Alright. Question 12. So question 12 shows you the variation of speed v, an object with time t. Which graph shows how the distance s traveled by the object varies with t? Okay, so right now we have speed time graph. But now we want distance time graph. How do we define speed again? Speed is
measure of how fast an object moves through a distance.
right, but like in equation.
Gradient over
Distance over time.
Okay, gradient of distance time graph, right? Or the rate of change of distance, right? So basically, you need to find a graph in which its gradient matched with this graph. Or what you're trying to do is you're looking for the integration of v, right? Because if you take derivative of distance, you get speed. So in return, or the other way around, you take the integration of speed, you get distance, right? So how can we look through this? Well, we can see right now we have velocity is the gradient, right? Gradient is increasing, which means it's gonna be a curve and it's gonna change, getting faster and faster, right? So first of all, it cannot be a straight line, okay? And since gradient is getting greater and greater, it's gonna go this way, not gonna go that way. If you go this way, gradient is getting smaller. But you can see velocity is getting larger. So first of all, gradient should, the graph should look like that. So that gradient is increasing. So this works. This is getting slower, so no. This here, the gradient looks like it's not changing, so no. We can also keep looking, and when it hits this point, gradient is the largest, right? Which means you should be the steepest, which is this here. And after it, gradient starts to getting smaller, so you're getting flatter and flatter, okay? You're getting steeper, steeper, here is the steepest, and then you get flatter and flatter. So steeper, steeper, and then flatter and flatter. So it's a shape of this. Any questions? Okay, Ma. Can we move on? Okay, question 15. Question 13. A ball is tossed vertically upwards with the speed of 5 meters per second. How many seconds will the ball return to its initial position? So if we toss this ball vertically upwards with the initial speed of 5, how many seconds does it take for it to return? Isn't it just survive? So let's do a survive. So we know that it goes up and then it goes down. We can divide it into two processes. If we look at going up first, so we know the initial velocity is 5, right? Final velocity is 0 because it needs to reach the highest point. Acceleration is
Negative.
okay, negative 10, minus 10, sure. So how long does it take to go to the top? T equal to delta V over A, right? So 0 minus 5 divided by negative 10, which is 0.5. If you go up, take 0.5. How much time does it take to go down?
0.5.
Also 0.5. So the total time taken for it to return to its initial position is just 1 second. Get it? We're good? Okay. And then question 15. The tennis ball is released from rest at height h above the ground. At each bounce, 50% of its kinetic energy is lost to surrounding. What is the height reached by the ball after the second bounce? If you still remember energy conversion, we know that without considering the air friction, the loss in GPE should equal to gain in KE, right? Because energy is conserved. But here, each bounce, it will lose 50% of its kinetic energy. Which means, if here, initially, at height h, right, you bounce here, and then you lose 50% of its energy. How high up can you go compared to previous one? Half, because here is mgh, and then you lose half of it. You can only go to mgh over 2 now, right? So that's your first bounce. You go to half. And then when you come back, you bounce off again. You lose another 50. You should get to the new height of the half of the half, which is h over 2 over 2. Right? So the second bump, the height you can go to is h over 4. Does that make sense? Any questions? Question 18. So question 18, the graph shows the variation with time t of the acceleration a of an object. Which of the following is the change in velocity of the object in the time interval to 0 to 4? So within this time interval, what is the change in velocity?
Area of the triangle.
Why is that the area of the triangle?
It's somehow like the because a times t
How do we define acceleration again?
v change of v.
Rate of change of velocity, right? Which means if we take the derivative of v, we get a. So in reverse, if we know a, we want to get v, we need to take the integration of a, right? So you already have the function of a, which is just a straight line. And then you're going to take the integration of this function from 0 to 4. You're actually calculating the area under the line, right? So in the acceleration time graph, the area under the acceleration time graph represents change in velocity, right? So you wanted to find out the change in velocity? Sure, let's find out. So this triangle is 4, 4. So 1/2 base times height, you get 1/2 times 4 times 4, you get 8, right? But is it positive 8 or negative 8? Is it positive 8 or negative 8?
Positive.
Why positive?
Because the graph says positive.
Because the graph is above x-axis, right? The graph is above x-axis. So this area is positive area. If it goes down, it's below the x-axis, the area is a negative area. So it's a positive change. Also, if you don't know, see, isn't acceleration the whole time positive? If acceleration is positive, that means speed is getting faster and faster, right? So your final speed should be greater than your initial speed. Do I explain it clear? Any questions? Okay, so that's question 18. Anything else? If no, we're gonna start with our new content. So basically, yes, that's a quick recap of your homework from A1. And for your reference, we already finished A1. Okay, we already finished A1 teaching content. It's just, yeah, we didn't go through everything on the PPT, but the rest of the content is just example questions. Okay, so homework for today, when you go back, is you're gonna 看一下啊，
做到没有选择。
actually finish the rest exactly，
对。
正好10页，好吗？10页，然后下周2交。Okay, you're going to turn in next Tuesday. Next Tuesday. Okay. Now let's look at A2. Okay, so what are we going to learn in A2? So in A2, we're going to learn Newton's 3 law of motion, force as interaction between bodies, that force acting on a body can be represented in free body diagram, which is our E9 second semester's content, if you still remember. Oh, wait. 你们依赖的时候是在做 rotation 吗？
我应该都
是 rotation。Okay, good. That means it's the same content. Okay, and that the free body diagram can be analyzed to find the resultant force on the system, and the nature and the use of the following contact force. Normal force is a component of contact force acting perpendicularly to the surface that counteracts the body. So what is normal force? Basically, any force that is perpendicular to the surface that of the contact surface. So for example, right now, if I do this, this glass will exert a normal force on me to support me, and this normal force is perpendicular to this glass, exerting on this part of me and pointing outwards. So if you can visualize a force, this force would look like this. Okay. If this force is getting larger and larger, so its length is going to extend. Okay. So that is contact force. The key feature for contact force or normal force is perpendicular to the contacting surface. And surface friction force. Okay, we're going to learn two types of friction: static friction and the dynamic friction. Alright, and the equations to calculate them, which is the coefficient of friction times the normal force. So we need to learn normal force first, and then we need to learn the coefficient of friction. And we're going to learn tension. Basically, tension is a type of force that is within the strain, okay? And it can only be stuff that can only be stretched, not squashed. So a rod would only also have tensions. So we'll see more examples. Elastic restoring force, FH, following Hooke's law. If you still remember Hooke's law is when you learn about what? Springs. Exactly. So we have a lot of springs here, right? So Hooke's law is when you learn about those springs. Okay. So the elastic restoring force, FH, is this one here. Right? Notice that FH equal to negative Kx. In MIP, we only teach you the size of the force, which when we learn Hooke's law, we only teach you how to calculate the size of it, which is just F equal to Kx. But in DP, you need to care about the direction as well. And there's a negative sign. Okay, there's a negative sign. All right. So, alright, and the nature, the viscous drag force, acting on a small sphere opposing its motion through a fluid as given by Fd equal to 6 pi eta RV, where eta is the fluid viscosity. We can do a demo of falling in water and falling in air, and how does different types of fluid has different viscosity that causes different drags on it. You can see it very clearly. We're also going to learn about gravitational force, electric force, magnetic force. Why do I put those three forces together? Are those three forces contact force? What is contact force? Contact force is the force that will exist when only two objects are directly in contact, right? But for gravitational force, electric force, and magnetic force, do magnets have to be directly in contact to have that force?
No.
No. Same for electric, same for gravitational. Even if I jump, I'm not touching the earth, there is still gravitational force acting on me to drag me back, right? So those are not the contact forces, they are called field forces. Field forces, because those are due to the respective field. Gravitational field, electric field, and magnetic field. And we're going to learn buoyancy. Okay, buoyancy. How do we calculate buoyancy? Using this FB equal to rho Vg, where rho is the density of the liquid, V is the volume of the water that has been displaced, okay, by the object. And linear momentum and resultant external force. This chapter 2 or A2 has a lot of content, I know, and most of you, according to my previous teaching experience, would suffer most from A2, but we will get through them one by one. So impulse, momentum, that's also what we learned in E9-2. E9 semester 2. Explosion and centripetal motion or circular motion. Okay, so a lot of stuff in this chapter. Okay, let's start with Newton's law of motion. So we already know this. We can jump. Alright, so let's look at what is force. Recall from MIP. Lucas, what is force? How do we define force? Not sure? 回去好好看一下书，复习一下哈，11年级底批了。Jaslyn, what is force? How do we define force in MIP? Well, that's Newton's second law. Sure, if you ask to define force, one way to define it is Newton's second law. But in general terms, a push or pull. Very good. So a force is a push or a pull measured in newtons, right? You either push something away or you push something back, right? So that's force. You either push or pull, measured in newtons. One force we're very familiar with is the force of gravity, also known as weight, right? That's our old friend, so we don't have to talk too much about it. And for push and pull, it implies the direction. So for gravity, right? Is it like a push or a pull for us? It's more like a pull, right? Every time when we're trying to jump or escape from our Earth, the gravity always pulls us back. It's not pushing us away to the outer space, right? It's dragging us down back to the Earth on the ground. So for gravitational force, it's a pull. It's a pull back. So if they have directions, of course, forces are vectors. Forces are vectors. The direction of the weight is always downwards towards the center of the Earth. Towards the center of the Earth. So no matter where you are, no matter you're in the north hemisphere or south hemisphere, your weight is always perpendicular to the ground, pointing towards the center of the Earth. So when you're at, let's say, when you're in North America, your force, your weight is pointing in this direction. When you go to Australia, your force is pointing in this direction. When you're in Antarctica, your force is pointing in this direction. Alright? Okay. Ouch. Okay. Alright. So, if you have a weight of 19 newtons, your weight can be expressed as a vector 19 newtons down. Right? Remember, vector has direction. So, W equal to mg. We don't have to talk about it too much. We have been very familiar with it. So, these examples, we don't care. But let's look at the free body diagram. So, we can sketch the mass as a point particles. For SL, you don't learn rigid body mechanics, which means most of the time, most of the scenario, you can treat anything as a point mass. You don't have to draw the shape, you don't have to consider the volume, the size, you can just use a point mass to represent it. But for HL, whenever you're dealing with rigid body mechanics, shape and size always matters, okay? You cannot treat it as a point mass. So, when we draw this, we can use a point particle, which is just a dot, and then we use an arrow to represent the forces. And this, if the only force acting on this point mass is the gravity, that is the free body diagram of it. That is the free body diagram of it. So, what is a free body diagram? A free body diagram is a force diagram that focuses on one object only. Okay, and this diagram has all the forces that are acting on this mass showing up. Okay, showing up. That is free body diagram. So, certainly there are other forces besides just weight, right? We also have, if you put a mass on a table, then the table stops it from moving. For example, this remote control, right? Table stopped it from moving. So, how do we do a free body diagram on this remote control? If we just focus on this remote control, then it has weight, and then it has normal force, right? Normal force, N. We use capital N to represent normal force. Any questions so far? No. Very good. Okay. For most of the time, the SL, we would draw the forces acting on the center of the mass. Okay. All right. But for HL, if it's rigid body mechanics, the position of the force also matters. Because let's say, if you exert a force in this and exert another force here, it will make it rotate. Okay. But for SL, if you don't consider the rigid body mechanics, it's okay to just draw all the forces at its center of mass. Note that the weight and the normal force are the same length. Same length implies that they're the same size, same magnitude, right? They can cancel out each other, right? Same length and opposite direction. They can cancel out each other. Any questions? Okay. The normal force is also called a surface contact force. Surface contact force. Okay. Now, why do we use R here for normal force? Well, because normal force can also be called reaction force. And then we can use capital R to represent it. The normal force is often called a reaction force. And so whenever you saw an R, and that's also perpendicular to the surface, that is reaction force. Where did we learn the idea of action and reaction again? Newton's third law. Newton's third law. Okay. So tension, for example, here can only be a pull and never be push. So we can use a strain to drag a box, right? And there is going to be tension within the strain, right? When you're trying to drag it, when you're trying to pull it, there's going to be tension within the strain. So friction, of course, on the other hand, would try to stop the object from moving. We're trying to stop the object from moving. So you're going to have tension and working as a driving force. And you're going to have a friction working as an opposing force, acting on the opposite direction of the motion. Okay, opposite direction of the motion. And friction is always parallel to the contact surface, while normal force is perpendicular to the contact surface. okay, normal force R is perpendicular to the contact surface. So those are the features of the force, okay? Some force, we have fixed direction. Can you give me an example of a force that has a fixed direction? Gravity. Gravity always points downwards, right? If we are considering a flat surface, gravity is always downwards, right? Okay. But there are forces that can change direction. For example, tension, right? If you drag it this way, sure, tension is parallel to the ground. But if you drag tension this way, then tension is always along the direction of the rope, right? Tension is always along the direction of the rope going outwards because it's a pull. It's never a push. It's a pull. Normal force can also change direction. It depends on the surface, the contact surface. If the contact surface is horizontal, normal force is vertical. If the normal force is a ramp, then the normal force needs to be perpendicular to it, which is not vertical. Okay? Okay. Friction and normal force are perpendicular to each other. And friction and normal force are surface contact force. That means you need to make sure they have direct contact to have normal force and friction force. Any questions? Action at a distance force is the same as field force. Which means it does not require direct contact for it to act. Alright, so we can draw a free body diagram. Weight is always sketched from the center of an object. Normal force is always sketched perpendicular to the contact surface. Friction is sketched parallel to the contact surface. Tension is sketched at whatever angle is given or along the direction of the strain. So let's do an example here. Draw a free body diagram of this thing. I'll give you 1 minute and then I'll check one by one. Get a notebook.画完再下课。Okay. You guys finished drawing the free body diagram? 我先 go around 看一看。基本呢？上物课不做笔记啊？这么自信。Okay, let's see. So we're going to draw the free body diagram, right? First of all, we always need to consider weight, right? gravitational force is always the number one force that you consider. So we always solve weight first. And then whenever there's weight, we need to ask ourselves, is there a reaction force? Is there a normal force that stops things from falling?
Yes.
Right? Yes, it's not falling, so there's gotta be a reaction force. And then we have this tension trying to drag the things to move, right? If there's no friction, then this thing is definitely gonna start moving, right? It is only the friction that would stop the object from moving, right? So when you're trying to push something, if it didn't move, that's because you're not pushing hard enough to overcome the friction, right? If you give it great force, it can overcome the friction, and then it will start to move. So it's friction as well. And finally, we have our tension force. So if we draw a free body diagram without considering the shape, then it's going to look like something like this. First of all, we have the weight, and then we have reaction force or normal force. We have friction, we have tension, we have tension. Any questions? So far so good? So far so good. Okay, so let's see, solving problems involving forces and resultant force. Now, resultant force, if you still remember, is the vector sum of all the forces adding up together, right? All the forces acting on one body, that's the resultant force. So let's look at this example, where we have an object which has a mass of 25 kilograms and a tension of 5, it should be capital N, Newton, and a friction of 30 Newton are acting on it as shown. What is the resultant force? What is the resultant force? I'll give you 1 minute to think about it. Let me change it back to, oops.
So,
Capital N. Okay, isn't it very easy? Alexander, what is your answer? What's the resultant force? 20 in which direction?
这个 direction right?
To the direction of the tension, which is the direction of the 51, right? So the net force is 20 Newton to the direction of the tension, But what about if there is an angle, right? If there is an angle, what we can do is we usually decompose the force. We decompose it to x-axis and y-axis, and then we apply the resultant force in each direction. So in x direction, all the forces added up together should equal to that. All the forces in y direction added up together should get you a y direction net force. Let's do an example here. An object has exactly two forces, F1 and F2. Apply simultaneously to it. What is the resultant force of the magnitude of the resultant force? So those two forces are perpendicular to each other now, right? And the resultant force is the vector sum of those two vectors. How are you going to find the magnitude of the resultant force? Pythagorean. So you move those two vectors so that they're connected head to tail. The head of the F1 is connected to the tails of F2. And then the resultant force is just from the tail of the first one pointing to the head of the second one. That's the resulting force. And then you have a right triangle where you can use a squared plus b squared equal to c squared to solve for the magnitude of F net, which in this case is equal to about 58 newtons. 58 newtons. Everything is good so far? Okay. What about the direction then? Hey, Darren. How do you got the direction for the resulting force? So in this case, how would you solve it? Tell me. Let's say this angle is theta.
So theta equals to tangent.
You mean tangent theta? Tangent theta equals 30 over 50. So you can solve for theta, right? Theta should be equal to tangent. Right? So pressure calculator, what's the angle? Thirty point 96 degree. (31 degrees) roughly. Okay. Questions? Good. What about this now? How do we do it? I'll give you 1 minute to think about it, and then I will invite students to share with us your solution. How do we find the magnitude of the resultant force in this situation, in this case? You need to actually calculate it, okay? Because when I ask you, I want to know how large is the resultant force. Are you down or not?
Yes.
结果不一样。现在这个 TI 的计算器一个要多少钱？1200，还是有点贵。要保管好，别掉了，这可是贵重的。
一部分是什么？是分啥？cos 28。
这边没有。
哦呀，我忘了 bracket。
What's your answer?
外面。
53，好像我们三个的答案都不一样。
等一下我没 bracket。
你们最后答案是多少？你们三个答案都不一样。
别急，等一下，我把它 bracket。别急。
我应该应该是69。
OK， 终于有一对对得上了。
计算机数学
多马斯算出来多少？
怎么回事？
哦，不是，我那个我少算了一个。
OK。
不算算错。
Vinci 算出来多少？69.3。
对的。
369.3。
OK。Vinci, can you share with us what's your method to find out the magnitude of the resulting force here?
So I first calculated the angle between F1 and F2.
Okay.
It's 90 minus 28, which is 62.
Okay, 90 minus 28, so 62 degree.
And then to make it easier, I just flipped it, like.
Okay, so you kind of like, or you flip the.
Yeah. And
Okay.
then I drew the parallelogram.
And then you do
and
this.
Arrow. Yeah, and then I found the angle. So I used 360 minus 2 times 62. 360 minus 2 times 62, and then divide by 2.
Mhm.
So 118, and I use cosine.
Okay, so a mathematician's way, okay, a mathematician's way. So, how's a more classical physics way to solve it? Lucas, what's your way?
Just split the 50 into x and y, and then just add the y component by 30, and then just Pythagoras.
Okay, so what you do is you first of all split this 50 into two components like that,
Y is sine c.
and you add f1y to f2, right? Is that what it's doing? And then, so if we move this to here, you're gonna about get this much in y direction. In x direction is just f1x. And then you do that, right? Okay, that's the second way. Both way works, okay, both way works. You can pick whichever way feels the easiest to you, feels most comfortable to you. You can pick any way you want, okay? You can pick any way you want. So here, classical physics way is to decompose F1 first. We can decompose it into two components, which is Fx, F1x, which is 44 newtons here, and F1y, which is 50 times sine 28, gives you 23 newton. And then you combine 23 to F2. You're going to get 53. And then you use Pythagorean again to get the resultant force, which is going to give you 69 newton. So the final correct answer is 69 newton. Okay? Final correct answer is 69 newton. Vinci's way is also correct, okay? Alright. Okay, let's move on. So we have solid friction. So recall that friction acts opposite to the intended direction of motion. For example, if I use my hand here, moving this way, what is the friction that acts on my hand by the table? To the right? Oh yeah, to the right. To you, to the right. Yes, to the right. Okay, because my hand to you guys is moving to the left, right? Okay. But what about the friction acting by my hand to the table? The friction given by my hand to the table is acting in which direction?
Left, upward.
So what is the friction acting on my hand?
Table.
In that direction, right?
Yeah.
Which is to the right. Then the friction applied by my hand to the table should be left. Why? According to the Newton third law, action and reaction, object A exerted force to object B in return exert an equal but opposite force back to object A, right? So the friction between my hand and the friction from the table to my hand and the friction from my hand to the table are a pair of action and reaction. Okay, so let's suppose we begin to pull a crate to the right and gradually increase the force. And we can plot the applied force. Actually, before I show you this diagram, I wanted to show you the simulation. Come on. Does it need a baby engine to load it? Oh, there we go. Okay, so right now, let me give you the sum of the forces I use and speed. Right now, if I, which is the dummy, apply a force to the box, can you tell the friction force right now how large? What about the applied force? So, is the box moving? Okay, so the box is still stationary or in the static mode. If I keep applying force, what happened to my applied force? I'm gradually increasing my applied force. And what happened to the friction force? It increased as well. No matter how large is my applied force, it always increases to balance out my applied force so that the box won't move. But there gotta be some limit, right? So let's test. What could be the limit? A? Let's do this again. Check what is the critical point. What is the limit right before the box moves? Is 120 the limit?
好像可以解项链。
Is 123 the limit?
Yes，刚刚120。刚刚
125 definitely moves, right? 123 moves?
嗯。
No. So let's look at 124.
刚刚124。
124 move 了吗？
对，
你再来看一遍啊。
可以输数字。
可以输啊。
不对，能点箭头的。刚刚。接下来。别想了，点20秒。
So 124 is the limit, right? So if I 123, why is the friction still 92?
Because dynamic.
Let's do this one more time.
Because it breaks.
Let's do this one more time. So, you see, friction force is 100, right? Before it moves, right? I increase it. Check closely. 122, still friction force. 123, still the same as that. But once I change my applied force to 124, what would happen to the friction?
It started to increase.
it decreases
Change
to 92. And no matter how large I increase my force, or no matter how small the force is, even now 74, which is smaller than 92, is still 92. What happened here?
Dynamic.
What makes the difference? Why is previously it can change its size, now it doesn't change its size anymore? What's happening?
It stops.
What's the difference? Like even now, 24 is way less than 92, it's still 92. What's the problem? Is this a bug? So if we plot our values, let me do this here. We can draw a graph. We can draw a graph. So here is the friction. Here is the applied force. As we observe, up until 123, no matter what force it is, friction force can always increase or decrease, adjust itself to balance out the applied force, right? It's always 1:1, so this should be a 40-degree line.
45.
45-degree line up until 123, right? Once it go up to 124, it will directly drop to 92. And then no matter how large your applied force is, it stays as 92. It does not change anymore. Well, what is the key difference before and after 123 applied force?
It's moving.
Before 123, is it moving?
No.
No. After 123, it is.
Moving.
So, here, what we call is this part, the friction here is what we call static friction. This here is what we call dynamic friction. So if a friction can change, can adjust its size, it is a static friction. If it's a constant, no matter how large force that you apply, as long as it's moving, it is a dynamic friction, right? It is a dynamic friction. Okay. Any questions? We're good? Okay. So, let's come back to PowerPoint. Okay, let's look at this dot by dot, one data point by one data point. So right now it is still static friction. So they're almost equal to each other up until they reach the maximum limit of static friction, and it starts to move, and it becomes dynamic friction. And then dynamic friction will suddenly drop, which means dynamic friction is smaller than the maximum static friction. Does that make sense? You will get a graph like that. You will get a graph like that. Now, during the static phase, the static friction force Fs exactly matches the applied tension force so that it can keep stationary, right? But as Fs increase linearly until it reaches the maximum value of Fs max, it will suddenly starts to move, and the friction will change its nature from static friction to dynamic friction. And so this friction will almost instantaneously decrease to the constant value Fd. The D here stands for dynamic, which is dynamic friction. And so you can get this relationship that static friction is greater or equal to 0, but at the same time smaller or equal to static friction maximum. But dynamic friction is smaller than the static friction maximum. Okay? Any questions for me? So far so good? And a dynamic friction is a constant. It won't change. It won't change. So, what exactly causes friction? You guys still remember anything we learned in MIP?
Yes.
So, what exactly causes friction? Okay. And just normal force?
The contact.
Area that
No.
What is counter force? Same magnitude, opposite direction. We mean balanced force. I don't think balanced force is one of the cause, but let's try.
When
touching
two objects.
two objects touching each other.
Touching each other.
and
One
there's
half.
Surfaces.
Touch each other.
You can only remember touching each other, right? So, people in manufacturing sector who work with metals know that if you smooth them or polish the two metal surface, then more strongly they stick together if brought into contact. So what you're trying to say, I guess, is the surface roughnesses of the surface. The roughnesses of the surface. Okay, and in fact, if simple polished in a vacuum, it will stick so hard that it cannot be separated because there is no gap between it for the gas to leak in or leak out. Okay, we will say that the two pieces of metal have been cold welded because they're so perfectly smooth that there is no space between them. Alright, so from the atomic level, when two surfaces come into contact, small peaks on one surface cold weld with small peaks on the other surface kind of look like this. And if we apply the initial sideways force like that, those cold welds would try to stop it from moving. But if the force is sufficiently large enough, then the cold welds will break and new peaks contact each other and cold weld. Okay? And if the surface remains in relatively sliding motion, fewer welds will have chance to form, and so we define the unitless constant, which is called the coefficient of friction, mu, which depends on the composition of two surfaces as the ratio of F friction over your normal force or reaction force. So how do we calculate friction force? Here I introduce you the equation with the coefficient of friction. This here you can read it yourself. Let's move. That friction is equal to coefficient of friction times reaction force or normal force. Okay. Usually, most of the case it's N. We use normal force letter. Well, even though reaction force and normal force are sometimes interchangeable, but conventionally we use N. Okay. Alice, would you please read this slides of 1, 2, 3, 4 for me?
Since there are two types of friction, static and dynamic, every pair of materials will have two coefficients of friction. 这个怎么读？这个
Mu.
mu s and dv. In addition to the roughness or smoothness of the materials, the friction force depends not surprisingly on the normal source law. The harder the two surfaces are squished together, this is what the normal force measures, the more the whole flows result. There the relationship between the friction force F, the coefficients of friction mu, and the normal force R.
Okay, very good. Usually we use capital N to represent normal force. Any questions for me? Okay. Mu. Okay, let's move on. Let's look at an example question. A piece of wood with a coin on it is raised on one end until the coin just begins to flip. Alright, so the angle with the wood makes the horizontal is 15 degrees. What is the coefficient of static friction? I'll give you 2 minutes to think about it. You guys can discuss with each other. You can think of it as this kind of situation. So you raise one end gradually, and this is the angle that it slides. So imagine the angle is about 15 degrees.哦，对了，一会儿我会把 HR 的作业发给你们啊。不多，我就不知道了。That's juicy.
Mu is equal to normal force, so that's total distance to the surface. So the answer is
其他就写。
Are we down?
Wait,
One more minute. There's slow one.
So it must be sounded relative. 一直上去，直到它 x 来回上来。Not make a friction. Force.
因为它只是问什么。
要不然它往下掉或往上飞。
非熟气。Okay. Any thoughts? If not, we're gonna talk about it. What did you get?
0.27.
0.27. How did you get that?
You use because it says the coin begins to slip, so that means that the forward friction force equals to the forward force that the coin has, which is
Okay.
the x component of the gravitational, the weight, and then downwards the slope, and then you have the y component, which is the normal force.
You mean like that?
Yes.
Okay.
And then you get the y component to be 9.66 mass, and then x component is 2.58 mass.
So this is 2.58
8 mass.
mass. Okay.
And then the y component is 9.66.
9.66 mass. Okay.
And then you just have, since it's begins to slip, so it's equal to the
Okay.
friction, so it's
So you mean
The friction force.
2.58 mass should equal to friction,
coefficient times normal force.
which is coefficient times normal force.
Yes.
Okay.
And you can find,
And normal force is
9.66 mass.
okay 9.66 mass. So mass cancel out. So coefficient mu equals to 2.58 over 9.66, right?
Yes.
And you get 0.27.
27. Yeah.
Okay, let's check answer. So first of all, we draw free body diagram where we have mass here, reaction force here, and friction force going this way. And Fy is the resulting force is 0. This is the y direction, which is perpendicular to the 15 degree. Okay, that's what we call the y direction. It's not necessarily has to be vertical. So y is Fy, the net force in y direction 0. Anybody can give me the explanation?
It's normal force. Normal force.
Y is, there is no resultant force in the y direction.
Because it's
normal
normal
force equals
forces.
to the gravitational weight, the weight force.
Is this normal force R equal to mg?
Yes.
mg
The x
cos
component
mg sine
on the y component.
mg, when you decompose it to the y component, which is in this case mg cosine 15, is equal to r. But why should mg cosine 15 equal to r? Because the thing is not moving perpendicular to the ramp, right? According to Newton's first law, if it's not moving in this direction, then the resultant force must be
Zero.
0. Similarly, when it just slides, just able to slide, that slide is also a constant motion. So that's the reason why in x direction, it is also 0. Because according to Newton's first law, if something moves under constant motion, constant velocity, resultant force should also be 0. So that's where you get friction equal to mg sine 15, which if sine 15 equal to 2.55, 0.255. Okay? And then you can relate those two. You actually got mass cancel out, g cancel out, you get mu is directly tangent 15, which is 0.268. 0. Or about 0.27. Okay? Alright, that's it for today's class. HL, do you want homework this week or next week?